Hello, and in today's PIC microcontroller assembly, we are going to be covering interrupts, and we are going to use the interrupt to toggle a LED on and off based on a button press. So if you press the button once, the LED goes on, you press it again, the LED goes off. Now let's go over the schematic. I have removed the button on RD3 from the previous video where we just used buttons, and then I removed the LED on RB0 and added a switch with a pull up to that, since the interrupt pin INT sits on RB0. Okay, now let's have a look at the datasheet. In section 14.11, we have the section that gives an overview of the interrupts. Now, for the PIC16F877 PIC microcontroller family, can have up to 15 interrupt sources, depending on which PIC microcontroller you are using. If you want to enable interrupts, you are going to need to set the GIE bit to 1, and that is located in the incon register on bit 7. And here they just say if it is set, it is enabled. If it is cleared, it disables all the interrupts on the PIC microcontroller. The individual interrupts can be disabled through their corresponding enable bit in various registers. Individual interrupt bits are set regardless of status of the GIE bit. So your flag bits will always trigger, it doesn't matter what the state is of the global interrupt enable. And then we have a specific instruction that is used, and that is the return from interrupt instruction. This basically functions exactly the same as a return instruction, except that the GIE, so the global interrupt enable bit, is re-enabled when this instruction is called. And here they say the INT interrupt, the RB port change interrupt, and the timer 0 interrupt is contained in incon register. The peripheral interrupt flags are contained in the special function register, so your PIR1 and PIR2 registers. When an interrupt is responded to, the GIE bit is cleared to disable any further interrupt. So when an interrupt triggers, the PIC microcontroller automatically clears the global interrupt enable. So this prevents you from having a repeated interrupt. Then I say the return address is pushed onto the stack and the program counter is loaded to 004. When an interrupt actually triggers, it disables the GIE bit. Then the code jumps to the flash position of 004. And 004 is the interrupt vector. And once an interrupt service routine, the source of the interrupt can be determined by polling the interrupt flag bit. So each interrupt has a flag bit. The flag bit indicates has this interrupt triggered or not. In the case that it has triggered, you have to test if the specific flag is a 1 or a 0. If it is a trigger, the flag will be a 1. If it's not triggered, the flag will be 0. And then just something of interest. For external interrupt events such as the INT pin, which we are going to use, or the port B change interrupt, the interrupt latency will be between 3 or 4 instruction cycles. So it can take actually quite a while before you see an event on the PIC microcontroller from an external source. And then they have a logic diagram of how the interrupts are wired. So for any interrupt to occur to the CPU, we need to have the GIE bit enabled, and then we can get a signal from any of the other interrupts. Now the interrupt we are going to be using is the INT interrupt. So the two bits that are required for INT is the interrupt enable, so the INT enable bit, and the interrupt flag bit. If you have an interrupt from a peripheral, then you need to enable the PEIE bit, and then you can get any of these. So you can see all the interrupts have 2 bits associated with them, with one being the enable and one being the interrupt flag. Now let's have a look at the registers. And then we get to the INT interrupt. This is the external interrupt on RB0, and it is edge triggered from either a rising edge in the option register bit 6 or a falling edge trigger. A rising edge trigger will look like this, and a falling edge trigger will look like this. So you go from 5 volts to 0 volts, and then your rising edge will be the opposite of this. Okay, and that is located in the options register. The registers we want to look at are contained in the memory organization in section 2.2, and then section 2.2.2 is the options register. The bit we are interested in is bit 6, which is the interrupt edge trigger. Since I'm using a pull up, I want to use the falling edge trigger on the pin. We are going to have to set this bit to 0 to get a falling edge trigger. And that's all we need to do in the options register. Then we have our interrupt configuration register. Now we have 3 bits in this register we are interested in. We have the global interrupt enable, which is bit 7. For a 1, it enables all the interrupts. We don't care about the peripheral interrupt enable. That is for any of the other peripherals. The timer enable we don't care about. We need the INT enable bit. We need to set that to 1 to enable the interrupt. And then we have bit 1, which is the INT flag bit. And if this bit is 1, then our interrupt has triggered. Okay, and that's it for the datasheet. Now let's get to coding. Okay, so now I have a base program here. I select bank 1 into the working register, and then move the working register to TRIS-B. Since RB0 is now a button, we need to have RB0 as a 1 and the rest as output, since the rest is all LEDs. And then I have a button connected to TRIS-D or D2. We set that as an input, then we select back to bank 0. We clear the B port, so we switch all the LEDs off, and then we clear the carry bit in the status register, just to ensure that there is nothing in the carry bit. And then we just blink the LED. Now, if you remember from the project setup, the interrupt vector is this. If we go to properties of the project, we go to the PIC-AS linker, then you can see p-int-vect is equals to 4 hex. Now, if we look in the memory organization, we can see 4H is the interrupt vector in the flash. Then we have the rectify instruction. So this effectively works like a return, except it enables the global interrupt bit. First register I want to work with is the options register. Then we go back to the memories organization. Then we can see in the memory organization that the options register is located in bank 1 over here. So in the section where we have bank 1 selected, we take our options register. So we use a bit set flag instruction. We can just copy paste this from the datasheet. Option reg bit 6. So that will set bit 6. We need to clear that for a falling edge interrupt. We clear the 6 bit of option reg to make it a falling edge interrupt. Now we check where our incon register is. Then we can see incon is a register that is mirrored on all 4 memory banks. So it doesn't matter which bank you select, you can always edit the incon register. The first thing we want to do is we want to make sure our interrupt flag is clear. So we take BDF, so clear. We take the incon register, bit 1, so that clears the flag. Now we want to enable GIE and incon enable, so bit 7 and 4. So we create a move literal to working, and then we create a brace. We bit shift that by 7. We OR that with another bit shift, and this time by 4. So this one enables the global interrupt enable, and this one enables the INT interrupt. Now we're going to use a new instruction. We go to instruction summary set inclusive OR with the working register. So it's going to be IORWF. So we want to inclusive OR with incon. So effectively what this does is it ORs the working register with the current file. So in this case it will be the incon register. So we are only manipulating the bits that we want to have enabled. And that will enable the interrupt for us. So now in our interrupt service routine, we are quickly going to check if we are actually triggering the interrupt. So we are going to do a bit test, skip if clear. So we take our intcon. So this is all now in the interrupt vector at location 4. We take our intcon. We go back to the register. We see intif. We want to check if that is clear. So if it is a 1, execute the next line of code. If it is not, just skip the line of code. So we are going to set the bit, so BSF instruction. Then we say port B, and we are going to set the 4th bit on the port B. And then we have to clear the interrupt flag because it does not clear automatically. You can also see here, must be cleared in software. But this is now just for testing that the interrupt is actually working. So we quickly program the PIC. We go to SBoard. Now see the one LED that is blinking, and then this button will trigger the interrupt. And as you can see, it triggers the LED to go on. Now, but the thing is, the LED does not toggle or anything. You are permanently stuck in this state. So now let's implement a toggle routine for this LED. We are going to create a new label above setup, and we're going to say this is int_ISR. And then the first thing we're going to do is we are going to do a bit test, skip if clear, and we are going to test what state port B bit 4 is in. So if it is clear, do something, then we create another label under that. So we're going to say LED_on. So do something when the LED is on for a label. We're going to say LED_off. So do something when the LED is off. And then we're going to say int_ISR_end and do something at the very end of our ISR. So in case the LED is on, go to the LED off label. And in LED off, we want to turn off the LED. So a bit clear instruction. So we just copy that bit set instruction and we turn it into a bit clear instruction. And then if this section skip, then we automatically fall into the LED on section. So this is going to be a S. And that goes to, we use a go to command, so a conditionless branch, and we go to the end of the ISR routine. And now at the end of the ISR routine, we want to BCF, so we want to clear. Actually, we can just copy this up here, and we clear the routine, and we say return. So we now return from our interrupt service routine, and up here where we test the flag, we just say call the interrupt ISR, and that is the LED toggle. So now we quickly program the PIC microcontroller. So now you can see the LED is off. We have one blinking. I push the button, the LED goes on. I push the button again, the LED goes off. These are very high quality buttons that don't need debouncing. They have an internal debounce circuit in them. You press, you unpress, and you can go on as much as you like. Now, I just would like to demonstrate what happens when you do not clear the interrupt flag. And this is going to be done in the simulator. So we are back at the code. We are going to remove the clear over here. We change our programmer to the simulator. We click apply. We set a breakpoint at startup or setup, whichever you want to call it. We go to Windows, Simulator, and we say Stimulus. We pick a pin RB0. Okay. We add another line, which is again going to be RB0. And we just set that one to toggle. So now we have an input. Now we can start the debugger, well, the simulator. I'm going to add another breakpoint over here just when the interrupt vector starts. Okay, and now we can let it run. We set our RB pin high since we are triggering for a low, and then we toggle it on and off. And you can see we are in the interrupt vector. If we step through the code, we call the ISR, we toggle the LED, and we return. As soon as I enter rectify, you would expect it to turn back to the main section of the code. But what happens is you start looping in your interrupt because your interrupt flag is not cleared. So we enable that again. We stop the debugger. We do a clean build. For some reason, I have to do a clean build every time I start the simulator. I don't know why. We run the debugger again. We set the port bin BI. We let it run. Then we toggle the pin, which triggers the interrupt. Then we step the code again, toggling the LED. Then we rectify, and you see it jumps back to wherever it was the last time in the assembly program. And that's a basic introduction to using interrupts on a PIC microcontroller with assembly language. A like, share, comment, and subscribe will be greatly appreciated. Thank you. Have a nice day.